What the heck?
Tagon.
Alright, so I'm going to do my best to try and complete the series that I'm doing on integrals over powers of the tangent function. If I don't, this will have to spill over into a fourth video, which will be considerably shorter than the last one, I'm sure. This one might run a little long if I try to put everything into it, but I'll do my best. So I'm going to continue right where we left off last time, what we've been able to prove so far about the contour integral over this particular class of integrals which have powers of the natural logarithm. And we're finally going to see how that actually ties into the original problem, because it's been in the thumbnail for 2 videos now, and I pretty much mentioned it once right at the beginning. So we'll be able to tie it in now. You'll find that this series of videos is mostly exploratory. It's going to really be the last little bit that's sort of more rigorous in some sense, and I'll explain when I get there. But for now, let's just continue right where we did last time, with our newly found integral. Can't do anything without the trusty cup of joe. Okay, so this is where we left off in the last video. If you recall, we did a contour integral over sort of a half donut shape in the complex plane to try and come upon a recursive definition of the class of integrals that we're trying to figure out, which were the integrals from 0 to infinity of this integrand here. And in the process, we had to figure out what the integral from negative infinity to 0 of that same integrand would be. And we were able to show that it is equal to the integral from 0 to infinity of the sum from k equals 0 to n of n choose k, the quantity I pi to the power of n minus k, times natural logarithm of z to the power of k, all over 1 plus z squared dz. And what this was is the binomial theorem representation of the quantity I pi plus ln of z all to the power of n. And this is what's going to allow us to actually evaluate what our original class of integrals was. So what we're going to do with this is we're simply going to factor out everything that does not depend on z, which happens to be the sum, right? The indices of the sum do not depend on z, n choose k does not depend on z, and I pi to the power of n minus k does not depend on z. So we're going to factor all 3 of those things out, and we're going to end up with the sum from k equals 0 to n of n choose k of I pi to the power of n minus k times the integral from 0 to infinity of the natural logarithm of z to the power of k over 1 plus z squared dz. And so this looks pretty simple in some sense because it's just a product of things and we'll be able to evaluate what they all are. But the striking fact is that we have this right here, which is exactly equal to I of little k, right? This is the integral that we're trying to evaluate, and we have now a way of writing the negative version of the integral in terms of the original integral, which is just great. So what we can do is we can just rewrite this as, and so now we can combine this with the regular integral that we had and set it equal to that value that we got using Cauchy's residue theorem in the previous video, right? Where the value that we know the contour integral has to take. And so I'm going to erase this, and we're just going to do that now. Okay. So this is what we were able to show so far. The regular integral that we want to solve for, that goes from 0 to infinity of that integrand, taken at the value n, plus this representation of the negative version of this integrand, of this integral, which went from negative infinity to 0, is equal to this, which is 2 pi I times the residue of this function at the point z equals I, which is what we were able to derive in the original in one of the previous videos. And so what we're going to do now is we're going to do a couple of cosmetic changes, we're going to move a couple of terms around, and we're going to finally solve for this class of integrals. So what we need to recognize first is that these are both versions of the integral that we're trying to solve for. So we can just call this capital I of n and capital I of k. So this statement is capital I of n, which is this integral right here by definition, plus the sum from k equals 0 to n of n choose k times I pi to the power of n minus k times capital I of k. It's the same function, just with k as an input, which is for this index here in the sum. This is equal to pi times I pi over 2 to the power of k. Okay? If we look at the nth term of this sum, that means we simply take this term here and plug in n wherever you see a k, and we simply take that term. Well, if I plug in n there, I get n choose n, which is simply asking how many different ways can I pick n objects out of a set of n objects. Well, the only way to take n things out of a set of n things is to take all of them. So there's only one way to do that, and so this n choose n is 1. And if you can see that we plug in n here, we get n minus n as an exponent, which is 0, and I times pi to the power of 0 is 1. So this is 1, this is 1, and we know that we can just plug in I of n for this. So the nth term of this sum is just going to be I of n. So we can actually pull it out and rewrite the top index as n minus 1, because now the sum is only going to n minus 1, and we can add the two I n terms together. So we're going to get 2 times I of n plus the sum k equals 0 to n minus 1 now, because we removed the nth term, right? We plugged n into all of it, sort of evaluated what it was, and removed it from the sum. So this is now looking like this, equals pi times I pi over 2 to the k. Okay, now, as you can see on the right side, we have pi to the k times pi, which means we have pi to the k plus 1 over here, but we only have 2 to the k, not 2 to the k plus 1. Well, I of n is the function we want to solve for, not 2 times I of n, so what I'm going to do is I'm just going to divide everything by 2, and then we end up with this. And now we're going to have 1 over 2 to the k plus 1, and we're going to have k plus 1 pi's and k plus 1 2's. So I can rewrite this like this. I just want to also clear something up. All of these powers on the right should have been n's. I'm sorry about that. So this should be I to the n times pi over 2 to the n plus 1. I hope that's easy to see. So let me just re-explain. So we started off with I of n plus this sum over also I of k, and k goes from 0 to n, and it's equal to this over here, which has n plus 1 pi's, right? It's pi to the n times pi, which is pi to the n plus 1, divided by 2 to the n, so not 2 to the n plus 1. But if you take a look at our sum, the nth term, if you plug in n wherever you see a k, you end up with just I of n. So we can take that term out, add it to this I of n, and get 2I of n. And then the sum only goes from 0 to n plus 1 now, because we removed the last term. We're not solving for 2 times I of n, we're solving for I of n. So we want to divide everything by 2, and what happens is we now end up with I of n, 1/2 of that sum that now runs from 0 to n minus 1. And now on the right-hand side, we have n plus 1 pi's, and we have n plus 1 2's. So instead of having pi over 2 to the n times pi, we now have pi over 2 to the n plus 1, and I've taken this I to the nth power and moved it out front. I hope that's obvious as to what I'm doing. Now we get to implement the fact that every single odd input to the capital I function, which is this integral that we're trying to solve, is always 0. Given that fact, that means we can essentially eliminate every instance of I of an odd number in this function or equality that we have here. So we can change all of our inputs to 2n. This way we can only attack the ones that we know are actually going to be anything other than 0. Every even input is going to give a non-zero answer, so we know for a fact that I of any odd number is going to be 0. So we can now eliminate those possibilities. So let's plug in 2n for wherever we see an n, because we only care about I of even numbers because we know they're not 0. So we plug in 2n, and we get I of 2n plus 1/2, and now it's going from k equals 0 to 2n minus 1, and we now get 2n choose k times I pi to the 2n minus k times I of k equals, now it's I to the 2n power. Well, I to the 2n power is the same as I squared to the nth power, but I squared is -1, so I to the 2n is the same as -1 to the n power. And now we multiply by pi over 2 to the power of 2n plus 1. Right? So that's what we get when we plug in 2n for I, but notice we have one more place where there's going to be odd inputs for this capital I function, and that's right here, because this index k is running from 0 to 2n minus 1, and that's every integer in between those two things. So we should try to come up with a way where we can eliminate any of the instances where I of k is evaluated in an odd number, because we know it's going to be 0. So let's see what we can do. Well, first of all, we know that 2n is an even number, right? But we know that we removed the last term from this sum, so this sum goes from k equals 0 to 2n minus 1. 2n minus 1 is odd, since 2n is even. That means that the 2n minus first term is going to be 0, because I of 2n minus 1 is 0. So we can actually end this at the 2n minus 2 term, right? Because that's going to be the next biggest even number, less than 2n, right? 2n minus 1 is odd, so I of 2n minus 1 is going to be 0, which means we don't need to consider that last term. But there's still all of the odd numbers between 0 and 2n minus 1. So what we're going to simply do is plug in 2k, right? But if we plug in 2k, we have to adjust our indices. So if we plug in 2k, we know that the bottom index is still going to be 0 because 2 times 0 is 0. But the top index now has to be n minus 1 because 2 times the quantity n minus 1 is 2n minus 2. If we only consider all of the parts where it's 2k, but we want the sum to equal the previous thing that we've got here, we need to change the indices. So we're going to plug in 2k for I as well, and we're going to end up with I of 2n plus 1/2 times the sum of k equals 0, and since we're exchanging k for 2k, the bottom index stays 0, and the top index is now half of what it was, which is n minus 1, and it's 2n choose 2k times I pi to the power of 2n minus 2k times I of 2k equals negative 1 to the n times pi over 2 to the power of 2n plus 1. Okay, I hope everyone's following so far. These are all just cosmetic manipulations. But we have one more to do, and we notice that this is I times pi to an even power. So what we can do is we can factor the 2 out of the power and distribute it into the product, and we get I squared times pi squared to the power of n minus k. But what's I squared? I squared is negative 1. Okay? So now all that's left to do is to solve for I of 2n, which means we just need to take this sum here and subtract it over to the other side. And what I'm going to do now is I'm going to erase everything and write this up top, and we'll see what we get. Okay, so this is what we've been able to show so far. The original integral that we wanted to solve, evaluated at an even power, is equal to 2 times that same integral from 0 to 1 over that same integrand, which is what we called capital I, and we're evaluating it at 2n, right? We've shown that capital I of 2n is equal to negative 1 to the power of n times pi over 2 to the power of 2n plus 1 minus 1/2 times the sum from k equals 0 to n minus 1 of 2n choose 2k times negative pi squared to the power of n minus k times I of 2k. This is what we've been able to show. And so now we can evaluate what this thing is finally equal to. Now, I'm not going to go through and plug things in and derive them now. I'm just going to show you what you get if you do plug them in. You can totally feel free to plug things in yourself and prove it to yourself. So we know from solving this where n equals 0 and doing the integral over and getting arctangent, right? We end up with pi over 2, which I'm going to write in a strange way as 1 times pi over 2 to the power of 1. And if we plug in 1, we know that we're going to get 0. Which is of course equal to 0 times pi over 2 to the power of 2. A little weird, I know, but just go with it. If you try to get I of 2, which means you have to plug in 1 for n, and you plug in everything, you end up with pi cubed over 8, which is of course equal to 1 times pi over 2 to the power of 3. And if you plug in 3, we know that you naturally get 0, which is equal to 0 times pi over 2 to the power of 4. And if you plug in, if you want to get I of 4, which means you have to plug in 2 for n, you end up with the fact that I of 4 is equal to 5 times pi to the 5th over 32, which is of course equal to 5 times pi over 2 to the 5th. If you plug in 5, of course, I of an odd number is going to be 0, which is 0 times pi over 2 to the 6th. And the last one I'll do is I of 6, which means you have to plug in 3 for n, and you will end up with 61 pi to the 7th over 128, which is of course equal to 61 times pi over 2 to the 7th. So now that we've been able to generate an actual sequence of these numbers that I of various integers evaluates to, we can sort of analyze them. So we can see that in each instance, we can, in fact, write them as a product of some integer times a power of pi over 2, and that power is always 1 more than the input. As you can see, half the time they are 0, so it may seem like sort of cheating to write it as a product of 0 and a power of pi over 2, but it's still true, right? So what we're going to do because it seems like the constant pattern is a power of pi over 2, we're going to just take a look at the coefficients of those powers of pi over 2. So I'm going to erase these things that we've got, and we're going to look at this sequence of numbers which starts at an index of 0. So let's do this. So we've plugged our integers into this formula here to get our I of 2 n's, and we know that all the I of odd n's are 0. All non-negative integers, so n is contained in the set of natural numbers and 0. We define the sequence an to be 1, 0, 1, 0, 5, 0, 61, 0, etc. So this was A0, A1, A2, A3, A4, A5, A6, and A7, and so on, right? There's infinitely many of these, because you can raise the natural logarithm in the power to whatever integer you want. And so what we're going to do is we're going to do a slight alteration of this sequence. We're going to multiply an times I to the power of n. And I don't mean I in this sense of this capital I mean I as in the square root of -1. So we're going to consider the sequence I to the power of n times a sub n, right? So we're simply taking whichever term it is and multiplying it by I of that same power. And what we end up with is, at the 0th term, I to the 0 power is 1, so we still get 1. I to the first power is I, multiplied by 0 gives 0. I to the second power is -1 times 1 gives -1. I to the third power is -I times 0 gives 0. And I think you're going to notice that at all of the odd indices, which give 0 in a of n, multiplying by a power of I doesn't matter, it's still going to be 0. So actually at all the cases where we get numbers that aren't 0, we're multiplying by a power of 1 or -1 anyway. So we're just going to actually get alternating positive and negative terms at all of the non-zero terms, whereas all the 0 terms remain 0 terms. So we get 1, 0, -1, 0, 5, 0, -61, 0, etc. So the terms that aren't 0 are now alternating sign, because any of the terms that we would multiply by an actual power of I, that doesn't just evaluate to 1 or -1, is being multiplied by 0, and so it does not matter. Now this is the part where it gets a little less rigorous, because what I've done here is I've sort of assumed that there's always going to be powers of pi over 2, but I think you can tell from this that that's definitely going to be the case, because we've got pi squared to some power here. This is going to give pi over 2 when you first plug in I of 0. But what I'm going to do now is I'm simply going to now consult the online encyclopedia of integer sequences, which is a brilliant resource when you come upon an interesting sequence. And so I plug this sequence of numbers, 1, 0, -1, 0, 5, 0, -61, 0, etc. Just those 8 numbers into the online encyclopedia of integer sequences. And they gave me sequence A122045, which is the Euler numbers, also known as the secant numbers. And so now we have a name for these. They're denoted capital E sub n. So from now on, I'm simply going to replace it with E sub n, because look what I'm going to do. I found out that powers of I times our sequence of numbers gives these numbers that are called the Euler numbers, and we'll see what they actually are related to. And we actually care more about our sequence than we do the Euler numbers. So what we're going to do is we're going to solve for it in terms of this. So I'm going to erase this now. We've shown that I to the power of the index that we are at in our sequence is equal to the Euler numbers. But we also know that all of the odd values are 0. And what we actually end up with when we get the Euler numbers is actually something very surprising. The generating function for the Euler numbers is actually the hyperbolic secant function. And the hyperbolic secant function is the hyperbolic equivalent of the secant function. But what's even more interesting is that if we simply divide both sides by I to the power of n, and we get I to the power of -n times the Euler numbers, we end up with our sequence, A sub n, which was 1, 0, 1, 0, 5, 0, 61, 0, etc. All the positive versions instead of the negative ones. We actually get the coefficients for the regular secant function. We can simply change the indices in our original thing, and we get I to the -2n power, which is -1 to the n power, right? So that's going to come out to -1 to the n times the even Euler numbers. That's what you end up with when you solve for our original sequence and only care about the even indices. And it turns out that this is the generating function for the secant function, so we can rewrite it as the secant of x. So all we did was we took our original sequence, solved for it by moving the power of I to the other side, realizing that all the odd ones are going to be 0, we just plugged in 2n, and I to the negative 2n is the same as negative 1 to the n, so that the imaginariness goes away, multiplied by the even Euler numbers. And because this is the sequence generated by the secant of x instead of the hyperbolic secant of x, we simply place this into the sum that we had before, and we now have the Taylor series for the secant of x. Essentially what we've been able to show is that I of k, which is equal to the integral from 0 to infinity of the natural logarithm of t to the power of k over 1 plus t squared dt, is equal to I to the power of negative k times the kth Euler number, which when you plug in even inputs you end up with I of 2k is equal to negative 1 to the power of k times the 2kth Euler number, the evenly indexed Euler numbers. What I have to do now is go back to the original question that we were posed and see if I can somehow relate it to this, because what I've realized is we probably don't even remember what the original question is. We've shown what we wanted to show so far. That's the sequence that we were able to derive. Those are negative integer powers of I times the Euler numbers, and again, all of the odd indexed ones are 0, all of the even indexed ones are non-zero, and that's how you end up with the Taylor series for the secant function. But again, remember, this was just a hunch based on the terms that came out of it. I have to now prove that the original question is somehow related to the secant function, and that's what we're going to do in the next video. So thank you very much for watching. This is actually going to be a 4-part series, and it doesn't matter. Goodbye.